Okay, I think we might as well get started. Do I have everything set up? So today we're going to kind of jump around a little bit. We were supposed to talk about constellation control segment. I have a lecture prepared by Major Steve Lewis, who's down in Colorado Springs. He got ill. So he said, I can't make it. Here's my material. Do you want to do it? And I was going to give it just because I think it fits in well. But at the same time, I think he's more interesting to hear because he's worked in two SOPs and see really what happens. And it's nothing we're going to be tested on. It's more just to give you some information what the current constellation looks like, why it's set up that way, what they do in the control segment. So I've asked him if he'd be willing to come up for another date, gave him a couple options. And then I went through the schedule and said, you know, what else do we have, which is more kind of a general information piece. I went all the way down, and we have this remote sensing space applications lecture. I said, okay, I'm going to swap those two around. And I think it does a nice job because if we talk about remote sensing, that really is a foreshadowing to some of the error sources that come into play, because that's what we look at when we're doing remote sensing. What we're not trying to pick up for the best possible GPS positions are those elements which we want to pick up for remote sensing, what's happening in the environment. And then space applications is kind of the same way. What can we do with the receiver? So I think they'll foreshadow a little bit when we get into these 2 weeks, you know, the week of 1024, the week of 1031, because those weeks are really on the error source we're going to see. So you'll get some perspective on that, talking about remote sensing and space applications. And then also I think that we've talked about the current homework 5, but we haven't really gone through it in detail, some of the M files, some of the Almanac files. So I asked Sarah to say a couple words about that, because this is really the last chance you have, at least formally in lecture, to ask questions about those pieces. So I've asked her to do both of those elements. So that's what we'll try to do. My hope is I can get Major Lewis to come back on this day to talk about constellation control segment, but I really offered him just about any lecture period other than the exam review times, so we can kind of fold him in, because I think he's a good speaker. I think he'd do a nice job talking about what goes on. So that's kind of the plan of attack. If you have questions on homework 5, let me get through remote sensing space applications a little bit, and we'll save the last 15, 20 is something like that, 25 minutes for going over the homework, see really what makes sense. So as we mentioned, homework 5 is due on Monday. No late assignments will be accepted, just because we're going to go over both assignment 4 and assignment 5 on Monday, talk through those as well as review what we did for homework 1, 2, and 3, kind of as a prep for the midterm. The midterm is going to be 9:30 to 10:45 on October 19th, next Wednesday, a week from today. The distance students are going to work the exam during the same time period, submit via Dropbox. Office hours haven't changed in any way whatsoever. Logistical questions at all as to what's going on? All make sense? Okay. Kind of jump into it a little bit. So really I have 2 different pieces today. One is on GPS, GNSS remote sensing, and the other is GPS, GNSS for space applications. And there's some overlap between these two. If I'm talking about remote sensing, I'm going to talk about GPS in space. So you'll see some overlap. I kind of have 2 separate presentations we put together by myself, Larson, and Axelrad over the years. But so you'll see some overlap. Usually we give them independently when we teach the class 3 times a week, but there's a little bit of a longer lecture period, so I kind of put them both together. You know, so the first question is how and why GPS plays an essential role in remote sensing. You know, the system data products are available globally. And everybody is aware of what happens with the satellites. You know, these satellites are orbiting the Earth. The system is constructed so we get position and time anywhere on the Earth. But an important piece that people often forget about is there's a huge network of reference stations scattered throughout the globe. These are all the IGS stations that you can see here with little blue dots. So all these IGS stations are taking measurements from satellite constellations. Majority are doing GPS L1, L2, but now they're upgrading those to do the different additional constellations, Galileo, GLONASS, Beidou. So you can have these measurements coming from the satellites. So not only do you have the satellites themselves, but you have this network of online reference stations observing those and observing the signal path as it propagates through any of the remote sensing pieces of interest, ionosphere, all those elements. So you can get that data locally, download it from these sites, and see really what has happened. So the global availability of the satellite data as well as receiver networks is quite important, quite powerful. You know, how and why? It operates in all regimes from surface to space. These are just a couple different applications. Again, I'm blurring space and some remote sensing. This is an altimeter, basically using GPS with a laser altimeter looking at sea level surface height. This is a UAV looking at weather conditions, flying with GPS. This is a C-130, NOAA operates. This is GRACE, basically the global mission, but it operates everything from sea level all the way up into low Earth orbit and above, as we'll talk about a little bit in space. So there's a wide range of spatial diversity where you can get these measurements and see where things really happen at. The other piece is not only if you are looking at the system, and many of you, I think in your careers, jobs, what you're going to have is you might not be looking at specific GPS systems, but GPS is critical because it gives you a time tag, location tag capability for any other measurements you might be taking. And if you use differential GPS, you can get that down to the centimeter level, but standalone GPS with no other radio links gives you down to a couple meters, which is great, and time down to nanoseconds. So you can synchronize time globally down to a level of nanoseconds using GPS. So even if you're not looking at remote sensing using the GPS signals themselves and what they're displaying, the capability to do time and position integrated with your other sensors is a pretty critical piece. And these are all different elements which you're using these buoys, everything else that goes forward. So really this is the key for remote sensing. I think this is Larson's comment, one person's noise is another one's signal. Because when we think about GPS and what we're doing is we're trying to get rid of anything that causes a disturbance in what that signal path takes to get from the satellite to me. Because we're assuming that's propagating at the speed of light, and any disruption in that whatsoever is causing us a problem because it's making the signal either look longer or having some distortion in how long it takes to get to us. So as a GPS receiver designer, I try to get rid of all those other pieces, but I can't do a perfect job. And what people have seen since the inception of GPS, GNSS satellite navigation is, some of those error sources can be valuable. If I don't want to just get a position and I want to look at some of the residuals that happen in here, I can get a lot of information out of that piece. So it's a very useful tool. So the environmental influences can be measured by way of changes in the signal characteristics. The code measurement, the signal-noise ratio, the carrier phase, all these pieces we've been talking about, and we'll kind of continue to elaborate in the later part of October. These error sources really can give some very distinct details. You have to remember that GPS is all operating in L-band. It's fairly weather independent. Doesn't matter if it's a rainy day like today or a bright sunny day. It's not impacted by atmospheric conditions very much. But what can happen to it? So these are three different examples basically that we're showing. The first one is basically the CDAN naught measurement for two different satellites as a function of TEC, total electron count. And basically what happens in the ionosphere, depending on what the ionosphere makeup looks like, you can go through and you can see what should be a very stable signal-to-noise ratio. You get these periods where you get high oscillations, and they correspond very well with what happens in the electron content in the ionosphere. So it's a huge thing. I can measure the ionosphere. Knowing what the ionosphere is doing, and many of you are remote sensing people, I defer to you to see really what that does. But I work on the receivers. How do I map this signal-to-noise ratio variation into a TEC count? Very big piece. Another one, if you're talking more about the neutral atmosphere, this is a plot for what they call radio occultations, and I'll talk about radio occultations in a little bit. But what we're showing here in red is the signal-to-noise ratio for a GPS satellite as I get a straight line height over the Earth. So when I'm above zero, that makes sense. I get a nice strong signal-to-noise ratio. And I'm also looking at how much Doppler I have beyond what I would expect. Because I always have the Doppler because I know what the satellite velocity is. I know I'm stationary. So I always have some kind of velocity that's going on. And the blue curve is what they call excess Doppler. It's Doppler I wouldn't really expect. And that's attributed to the atmosphere, the neutral atmosphere. So as the signal sets, it kind of channels the GPS signal through the atmosphere. And based on this additional Doppler or frequency change I see, I can go through and get significant detail about what's happening in the atmosphere. The last plot. This is over at Marshall, a fairly local site. And that's looking at the CDAN naught or signal-to-noise ratio as a function of time. And that should be a very stable signal. But what you notice here, you see these oscillations. And these oscillations are very curious for a long time. And again, we've done a lot of work at CU Boulder on all aspects of GPS and GNSS, particularly for remote sensing. This is some of Larson's work. Where are these coming from and how can I really use these? And I'll talk about that a little bit later in the presentation. Because I would expect as the signal-to-noise ratio changes, We talked about the antenna pattern. I would get a very stable increase in signal power, but I see this oscillation, particularly at these lower elevations. So I'll kind of foreshadow that and allude to that a little bit later in the lecture. But the key piece is all these disruptions and what I want GPS to do can be used to sense the atmosphere or the environment of what's going on around us. So it's a pretty big deal. Earth surface and gravity. Gravity is a key piece. Another piece is these geodetic receivers. We talked about the IGS sites. This is the PBO database, and they're really looking at plate tectonics, plate shifts for what happens. This is a typical site, very remote locations, running off solar panels to see what happens. And they're looking at the plate tectonics, how many things shift. And this is Concepcion, basically when they had an earthquake. And you can see GPS is measuring the displacement, east, north, and vertical. Very, very quick displacement in terms of fairly significant when you have an earthquake to see those kind of pieces. So PBO is really looking at plate shift tectonics on a carrier phase level, very high accuracies to see what happens, and GPS is a key piece for this element. This is the GRACE mission measuring gravity and really looking at ocean rise, global mean sea level to see really what happens. Again, a space-based application, but using GPS to go through and look at what happens to the global mean sea level and ocean mass, and you can infer different pieces. We had a very high precipitation basically right here compared to normal years, and it kind of run off and drop. So it really gives a lot of different elements. This work is done by Steve Niram's group, working with GRACE data. So again, here local at CU Boulder. A couple slides ago, I talked about these oscillations, and we're going to talk about this in some more detail as we get into the error sources. But we use GNSS for conventional PNT, position, navigation, and time. One of the big problems, one of the hardest ones to deal with are reflections. Because if you think about what goes forward in GPS, I think this is a good depiction here, but just to be clear, if I could draw my satellite up here, this is my direct line of sight signal, which is coming to my antenna. And that's the signal that you really want, because that is the exact line of sight. You know that this is propagating at the speed of light. But the signal doesn't only propagate there. You know, you have many rays of the signal coming all out, and it's very easy to get a reflection which can bounce off different surfaces and enter the antenna. We talked about this a little bit at the beginning, but GPS is an RHCP signal, right-hand circular polarized. So when a signal reflects, it usually changes the polarization, this is from a reflection, into an LHCP signal. So left-hand circular polarized. So you get a change in polarization, and the antennas are designed to kind of reject that because we don't want any changes, because this path here has a longer time delay to get to me. So I'm going to estimate the satellite is further away, cause me a problem when I'm trying to get my range to that satellite. So the problem is I really don't want to see that. So okay, we'll do these RHCP antennas. So when we have an LHCP signal, let's get rid of that. Let's see really what happens. And if you look at it, the RHCP works pretty well for signals which are kind of where you're looking for, up above, 20, 30 degrees. But when you're trying to build an antenna, just because of the physics of trying to put that together as I understand it, it's harder to get that strong RHCP signal kind of on these lower elevation angles. So when the satellite is at a low elevation angle, particularly these periods in here, I'm letting in more of the LHCP signal, and it's mixing with my RHCP signal. So I have this mix of my direct signal coming in and a reflection signal coming in. And as that satellite changes, there's a phase change between the direct signal and the reflected signal, which causes this oscillation. So okay, that's a problem. It doesn't help too much. My reflected signal is significantly weaker because not only is my antenna trying to reject it, but it had to travel along a longer path. It's getting a reflection off the surface, but enough of it still gets into my receiver that it causes a problem. I get these oscillations, so it disrupts what my position is going to be. So one thing that's very interesting, if we talk about this, is can we get any information from this? Because Professor Larson, when she was looking at this initially, she saw, hey, this is very repeatable. I see the same thing day to day, but if I look at that data over the course of a year, it's really not the same. What's changing this so that I can see this from one day to the next? I get a very similar frequency of oscillation, but I look at it in January versus if I look at it in June, it looks quite different. Any idea what that could be? Guesses? Snow, okay. So maybe I've mentioned snow before, so it might be an easy question. But basically, if you think about what happens, is if I think about what's going on around the antenna, this surface height is going to change, if it's snowing, if it's wintertime. So if I get some layers of snow coming in here, basically the frequency of what happens is going to change because the phase relationship between my direct signal and my reflected signal, if you can see with all my scribbles on this page, it changes a little bit to what that phase relationship is. So if I skip ahead to the next slide, this is a picture of what happens over a 5-year average with a snow sensor, some in-place snow sensors, as well as what we can see with GPS. And you see strong correlation between those two. And so she went through and looked at the algorithm we could look at. What is the frequency of these oscillations? Because the frequency is directly related to the height of the antenna above the surface. And look at from this is an Iwat Ridge. I can tell you how deep the snow is just by looking at the GPS reflections from an existing station. And again, I talked about how we have these existing stations all over the world. So if I can go through and I can get a snow measurement from it, wow, that's a big deal. That's a big plus. And again, I'm not a remote sensing person. I'm a radio person. And my first question was like, who cares? I mean, why measure snow? But so then I looked at how people measure snow. What they have to do is they have to send people up with snowmobiles, and they put sticks in the ground, and says, okay, that's the snow depth here. Very manually intensive process. And I said, okay, well, because you have that much snow, who cares about that? Everybody out west, because all your water comes from the snowpack. So you really have to have a very good idea how much snowpack is in both the Rockies and Sierra Mountains, because that's giving you all your snow sensor, all your water conditions for the next coming months as we get melting to the summer. Bless you. So snow is a very, very big deal. And again, I'm more of an electrical engineer, receiver designer. So I saw this and I said, okay, well, that's great because you can use these sensors that are already in place to have this work. But if you look at what happens, and I'm going to erase this from my slide. Hopefully everybody gets a perspective on this. If I look at one of these installations that I showed back here, anybody have any idea what one of these installations cost? Guesses? Speak up, yeah. The receiver alone is like $6,000. I mean, it's a very expensive carrier phase, all constellation kind of receiver. The antenna might be $2,000 just by itself. Then you have the solar panel, infrastructure, so you can get the data back. So they're not cheap in any way whatsoever. But again, their primary purpose is not for snow. Their primary purpose is for tectonic plate shift, some other kind of piece like that. So they're installed for another application. So if I get snow for that for free, hey, that's wonderful. I don't have to pay anything. I have a snow sensor in all these locations. That's great. But if I think about this, and again, being an electrical engineer and kind of thinking of what happens, I'm thinking, well, this antenna, that's really designed to reject all these LHCP signals from this path, as well as all these LHCP signals from this path. So really what we did is that, and these antennas are $2,000. I said, if I just use a simple cell phone antenna, which is on the order of 10 cents, and my cell phone antenna, it doesn't know what direction the signals are coming from, and I don't really put the polarization in there because I want to get any signal energy I can. Well, then I use a cell phone antenna, which is usually linear polarized. Well, it gets a signal from all locations as well as a reflection, so it's much more receptive to this reflection coming off the ground. And if I look at what that CDOT nut looks like, I get these huge oscillations all the way over the path of the satellite, because I'm getting that reflection from the ground as well as from the direct signal. Now my antenna went from being $2,000 to about 20 cents. And I don't have to use a $6,000 receiver anymore. I can use a mass market receiver, which is in this guy, to give the same conditions. So I can build a very effective snow sensor for tens of dollars. But of course, it's not deployed everywhere. So what are you looking for? You're looking to try to leverage all the systems that are out there. You can get snow during that. But if you want to build a snow sensor and put it in remote locations, you can do it very inexpensively using these GNSS signals. So again, a concept that really wasn't considered anywhere before, but you can bring into play by thinking, okay, how can I use these error measurements and even tweak my receiver design to improve upon those pieces to see really what happens? So I think it's a very cool application. So in addition to snow depth, you can look at soil moisture, because if you think about what soil moisture is, if your soil is very dry, it's not very reflective, it kind of absorbs the signal. Or if I have a wet soil moisture kind of day, GPS doesn't permeate the soil very much, but I get very much stronger reflections. That amplitude of the signal coming back is going to be stronger, cause more phase oscillations, see really what happens. Vegetation, If I have vegetation, kind of a scattering surface on top of the soil, it kind of scatters that reflection. So I can see vegetation as well. So all these elements, me as an electrical engineer designing GPS receivers, are like, who cares? Very big deal in the remote sensing community. If I want to know how vegetation is growing in all these remote sites, it's really an important big deal. So just to be aware of those elements. And it's all coming as a byproduct of the GPS signal. Surface reflection on the signal, we talked about this a little bit before early. This is another project I have been involved with. If you're looking for what the height is, I can do a very good job using a passive bistatic GPS reflectometer. So most radars are going to put down a signal and look for it. I can use all the signals reflecting off the surface to tell me what the height is all around. And there's so many GNSS satellites, I get a very good picture, terrain kind of database kind of picture to see really what happens. And the result, if I talk a little bit about this, we talked about this before, if we look at the wave height, if this is a very calm surface, the sea is very flat, I get kind of energy from one particular point on the surface. As the seas get rougher, I get more waves, everything else, I get kind of a scattering. So I get energy from different locations. So I can highly correlate what the scattering surface looks like with what I get in my receiver. And a scattering surface is really based on what the wind speeds are going to be. So as opposed to doing dropsondes or any other kind of remote sensing elements, I can look at my GPS reflection, purely passive, not dropping any sensors or anything else like that. What does that reflective surface really look like? Is it coming from a scattered surface where all these different locations are giving me reflected energy, or is it just coming from a very flat surface where all my energy is focused in one main path there? I can tell you what the wind speeds are going to be. And as a result of that, there's a Cygnus mission, which is supposed to launch this year. I don't know if it's got pushed back to next year. But it's a science goal to look at GPS reflections, mainly to study typhoons, hurricanes, to try to estimate those wind speeds as opposed to find a NOAA P3 hurricane hunter right through them and doing dropsondes. So it's an experimental mission going to find L1 payload looking at GPS reflections coming off the surface of the Earth. So this is a big deal. Think about GPS signals on the surface of the Earth are very weak. Now you're flying out in space looking for a signal coming down to the surface of the Earth, reflecting off whatever kind of reflection coefficient you get and going back into space. And what does that really look like? So it's a very interesting mission. You'll see really what comes of it. But all these are remote sensing. Everybody uses GPS for position, navigation, and time, but all these remote sensing pieces come into play as well. So it's kind of a cool, important detail. Sensing the neutral atmosphere, this is a work that we've been involved with as of late in my research group. And it has to do with this concept of, hey, I'm on the surface of the Earth somewhere, I'm using my GPS satellite. But really what I want to know is I want to know what happens to the neutral atmosphere kind of surrounding the Earth and see really what happens. So this concept of radio occultation, which has been around for a long time, it's used to sense the environment of different planets when we send satellites to different planets. What you're doing is you're flying a GPS receiver on a low Earth orbit satellite, much below the GPS constellation. And the GPS satellite is using the LEO satellite is using the GPS constellation to get its position, but it's also looking for this excess Doppler that we had talked about before, where the atmosphere, depending on the makeup of it, how much moisture, water vapor, temperature, pressure, humidity, will channel that GPS signal. So it doesn't really have a line of sight anymore, because the line of sight would be going through the Earth, but it channels that signal so it goes through. Supposedly it's one of the top 3 inputs to numeric weather prediction models to see what this data really shows. And a couple missions have flown. Cosmic is a big one to show really what happens with that. I think I have some more pictures of that coming up. So that really is sensing the neutral atmosphere. Another piece of Christine Larson's work, she's done a lot of incredible work on remote sensing, is you can imagine that this was a volcanic plume. And the concept is fairly simple, basically. So if you have a volcanic plume, what she's showing here is when the event began, when she saw a change in SNR, and kind of when the event ended. But is there a way to detect where these plumes are going, what's really happening with these plumes of ash which are coming up? And the concept, nobody had thought about it at first, but she's been giving a lot of thought to these pieces. So I have my volcano. This is my rough attempt at drawing anything whatsoever. And so I have GPS sensors all over the place because we have this whole network of stations. So as the plume comes up and the ash comes in here, my signal's coming down from the satellite. Basically, I have to propagate through this. This is an obstruction. It's an attenuator of what those signals really look like. So by having a whole dense network of really what happens, I can say, okay, that one's in the clear, but as this plume evolves, manifests itself, you remember what happened in Iceland a few years ago? They were trying to track where the plume was, see really what happened. That's not an easy thing to do. But by having this network of GPS stations and looking at the attenuation because of all this additional mass, which is blocking the signal, I can tell you what direction, have good predictions as to where the plume is going, where is it safe to fly, where is it not safe to fly, see really what happens. Just by looking at the signal-to-noise ratio of this reference station and how it changes from day to day. Because again, the satellite repeat period is about 24 hours, so every day I see the same satellites. So if my signal-noise ratio changes, what caused that to change? It should be the same day to day to see really what happens there. So again, another unique application to see really what goes forward. This is a GPS IO satellite. I kind of explained what this plot was. This is the excess Doppler. When we are very high in the sky, we get a nice strong signal-to-noise ratio. The Doppler is exactly what we would predict it to be mathematically. But as that signal kind of sets and we still try to track it, hey, we're trying to get energy from that. Well, I'm getting some energy from it to see really what happens, even though it's below the horizon. Well, I'm getting this excess Doppler, and there's an able transform. I don't know all the details, but you can map that into the conditions you're looking for numeric weather prediction models to see really what happens. And this is kind of what happens. You're trying to get the makeup of that component as you take these measurements. So these are our satellites. Cosmic is a constellation which was flying. It's about I think it's been around since early 2000s, 6 different satellites looking at these ray occultation measurements. Again, the satellite has to use GPS to figure out where it's at. That's a key piece. But then it has this forward and aft looking antennas looking at both sides of the Earth. And if you look at 3 hours of coverage, trying to get this neutral atmosphere, what is it? Pressure, temperature, elements of the neutral atmosphere, I get a huge sampling of that from these 6 satellites, just over 3 hours of coverage. Massive input to numeric weather prediction to see really what happens with that. Cosmic 2 is a mission that's coming up to see really what happens. There's been some commercial entities which said, hey, this is a very valuable piece of data. I don't need a huge satellite to do it. So it's one of those pieces where people can say, okay, can I commercially market some kind of small CubeSat kind of mission that could develop this kind of data? And there's 3 or 4 companies trying to develop this to do that quite effectively. Sensing the ionosphere, space weather. Again, the ionosphere is a very big element for radio communications, satellite communications to see really what happens. Using all this ground-based network of GPS receivers, which are shown in the dots on this plot right here. I can go through and show what the total electron count is or get an estimate of what the total electron count and how that evolves over time. This is critical for systems such as WAAS or aircraft landing. When I have to say I want to use my landing system for GPS, if I'm getting delays because of the ionosphere is slowing my signal down, so the range of the satellite looks longer, it's distorting my position between one aircraft and another aircraft, it causes problems, particularly on the landing system. We need accuracies on the order of meter, sub-meter kind of levels to see what happens. So all these are different ways to measure the ionosphere, space weather, and GPS has proven invaluable in that because it's insensitive to atmospheric conditions, but ionosphere, space weather, it's a big impact for. Traveling ionospheric disturbances, this is kind of interesting. Earthquakes, tsunamis, volcanic eruptions, meteor impacts, underground nuclear explosions, they all cause ripples in the ionospheric layer. And if I can track what's happening with those ripples, I can have these kind of detection capabilities because they all have a different signature. So if you really know what's going on with the ionosphere, you can detect these different elements and see really what happens. There's even been talk about, can I detect earthquakes in advance because things happen in tectonic plates to see these pieces. So there's been a lot of research in that area as to how you use the ionospheric maps to go through and say, what's happening, what kind of signature, what does this event look like when I see the ionosphere? For right now, you can just have data, oh, we had an earthquake here, what did the ionosphere look like, so you post-process that. And then if you have some real-time monitoring, can you use that to do any kind of prediction or see really what happens? Very interesting pieces. So that's kind of a summary on the remote sensing piece. Basically, what's big about it is most things have been done with GPS, and that was our constellation of anywhere from 24 to 30 satellites. And if you think about what's happening now, we're adding 3 more constellations, GLONASS, that's kind of always been there, but it hasn't been a real focus. But Beidou and Galileo with its better clocks. So we have 80-some satellites visible in any location on Earth. Receivers are much cheaper to see really what goes forward. We can fly small satellites, UAVs, what can happen. And then the integration with different data types, models, operational systems. People are looking at other signals of opportunity. You know, people have talked about using Sirius radio and other signals that look like that. Can we use iridium for these pieces to see what goes forward? But the whole purpose here is just to expand it. GPS, yeah, it gives you position, navigation, and time. You're likely to use that. But if you look at the error sources, and as we get into error sources, think about what that's telling you. How can you use that and kind of get information for remote sensing applications? Questions at all? Does that kind of make sense? Hopefully it motivates things a little bit, thinking about the error sources. Okay, so I'll shift gears a little bit. Some images, references, I'll post all the slides. So space applications. And again, there's some overlap here. But again, this is an aerospace department. Many of you are aerospace students. So how do we use GPS in space? And everybody said, okay, coverage for spaceborne platforms. You know, if you think about the GPS orbits and a LEO orbit, you see many different satellites, but many things that people forget is if you look at the antenna pattern, which I think I have in the next slide, this slide. This is the antenna pattern of the Earth. And I think the Earth is, from the LEO orbit, what was it, 35, 40 degrees. So first question, this is good exam prep. Why do we have this part? So let's say this is the envelope of the Earth. Why do we have this shape of the antenna pattern? You guys remember? Yeah, so exactly. So if you think about what the orbit is, if I have a satellite directly overhead, I would have the same power as if that orbit is coming in from the side to that location. So it's supposed to give you equivalent power whether I'm looking at a satellite overhead or a satellite on the side. Try to give you balanced power in that regard. That works out most of the time. If I jump back, okay, this is just kind of a fun question. So if that truly is the case, and I erase this piece here, and I look at my CDN naught as a function of a satellite elevation pass, how come it's not flat all the way across the pass? Trick question. Do you guys know? Guesses? Because I showed the antenna pattern for satellite. It should give me equal power here and up here. But if I look at what I receive, I get this variation, about 10 dB. Please guess.
It has to propagate through a lot more atmosphere and mass.
Decent guess, but not right. It's a good one. Other guesses?
Antenna pattern of the receiver.
Pardon me?
Antenna pattern of the receiver.
Exactly. So most of that coming from the antenna pattern of the receiver. The receiver knows that, hey, I don't want to pick up signals below 10, 20 degrees because usually I get a lot of reflections, a lot of junk in there. So I basically try to look for satellites above 20 degrees. So coming, and I can't just make a hard cutoff right at 20 degrees. Everything's going to be perfect. So I got to kind of rope that in just a little bit. So most of this variation is coming from my antenna pattern, my receiver, where the satellite antenna pattern is trying to model that. But there is some additional attenuations, particularly as I go through the atmosphere, everything else. But most of that is coming from my antenna pattern, the receiver. Okay. So if I look at it, though, this is my envelope of the Earth. I have a considerable amount of energy outside of that envelope, which I could basically use for geo-type state measurements and see really what happens beyond the internal of the GPS constellation. If I'm talking about doing it LEO, I can usually see 10 or more satellites typically. The dynamics are very well known, very well modeled. But the problem is I have a rapidly changing geometry. If I'm in LEO, I'm zipping past these satellites. I have a couple of works that we've done for radio occultation. But my satellite constellation is changing very, very quickly. The velocities imply a high Doppler rate. Where do I put my antenna? Because I kind of want to get these signals, and I'm going so quickly through the LEO orbit to see what happens. There's very little atmosphere to deal with, except I'm very low orbit. No troposphere, but there's more radiation I have to deal with. So if I'm trying to do GPS in LEO, this is really what happens. If you are designing CubeSats, you can go to any of the major vendors, at least a couple of different major vendors. Novotel, for example, is one. Their receivers are a few $1,000s. And if I buy it off the shelf, it won't work in space because of this altitude velocity restriction. If I can prove to them that, okay, I'm a suitable user, I'm allowed to use this person, they will give you a new firmware you can download on that receiver, which will remove that altitude velocity restriction, as well as open up the Doppler search space so you can use it. But you can put a GPS receiver on a satellite for thousands, on the order of thousands of dollars to see really what happens. If I compare that to going to the JPL Trig Blackjack design, that is over $1 million receiver because for this remote sensing, it's designed specifically for space, has a redundancy where the Novotel, is never designed for radiation tolerant kind of work. But you can get a few $1,000 L1 only receiver that kind of works in LEO orbit. So I talked about the antenna pattern of the satellite. That's what it looks like. This is to give you constant power, but you have a lot of energy outside the main beam, which you can use for high Earth orbit, geo kind of positioning. So just a historical perspective, and I don't have the numbers, I don't remember numbers off the top of my head, but if you go back, one of the first GPS receivers flown was on Landsat 4 in '82. The constellation was barely populated in '82, but I forgot what the mass was, but I knew it used more than 45 watts of power, basically, just to fly that receiver. And there's a receiver that's flown out of DLR, which is the equivalent of NASA in Germany. Phoenix, they used sub-watt, and it was very small and gave very, very good accuracies. Improved to 1 millimeter per second velocity, kind of see really what happens. So just how things have evolved over time, but that's true with any technology. Precise orbit termination is a big deal. We do a lot of work with that here at CU. GPS is a key piece. 2 missions, Topex Poseidon one's here. Grace is a very popular one here. This was using a Motorola Monarch receiver. This is using JPL Blackjack design. POD, it's worth talking about. A lot of the classes here we have for grad classes really cover precise orbit determination, but you're recording high precision, dual frequency measurements, carrier phase pseudo-range data. You're working with the ground network stations to remove some of those errors we have talked about. One of the key courses here, 57, you're dealing with the Kalman filter you developed for doing this precise orbit termination. Higher gravity fields, drag models, solar radiation pressure, how all these elements impact my orbital estimation using the data I get from GPS. So see really what happens. Formation flying has been another big one too, in '98, and also some different missions that are happening now, trying to keep satellites at very close proximity to each other, knowing exactly where they are. GPS is a key technology, enabling those kind of missions. Attitude determination, we talked about this before too. It's happening on the NOAA aircraft. We talked about how you're looking at reflections coming off the piece, but you can use attitude determination for GPS, 2 different missions. The ISS has a funny software receiver on where, as I gave you the raw data, I have raw data collected on the ISS just because they have another data collection platform right there too. It's kind of fun to look at and see really what happens. But it's a tool you can use to play with some of these pieces. Remote sensing, not going to go into this again. This was the GPS, MEDOPS, and Cosmic, but really radio occultation is a key piece for weather prediction and what happens now for using GPS. This is the antenna, I think, for TRIG, a multi-element antenna. It has to get very high directivity. Look at these pieces. TRIG is the receiver developing in the Cosmic 2. But everybody has recognized the importance of GPSRO for temperature, water vapor, and electron density content. So it's such an important piece now of what really happens. But you have to use the upward antenna to get POD. Then you have these limb point antennas that measure amplitude and phase of the GPS signal. So, and this able transform is a key element in resolving those pieces. Bistatic radar, again, we alluded to it before. That's when the aircraft is flying, you're looking at reflections coming off the surface of the Earth. This is kind of giving you a delayed Doppler map, which kind of helps you interpret wind speed and what the wind speeds from are those pieces. That's more remote sensing element. CubeSats, we talked about what the Novotel can do. These are 3 recent success stories. CanX2, that's flying a Novotel receiver. I don't know what the other ones do, Fast Track and Reax. I'm not sure what the other receivers are. But Surrey makes a receiver on the order of tens of thousands of dollars you can fly, which has flown in space. So it's not difficult to get a GPS receiver for space these days. It's very difficult if you want multiple redundancies. Not very difficult, but maybe very expensive. If you want multiple redundancies and see really what happens across the board when you want to fly this. And that's really not applicable for CubeSat nanosats. So not only have we done GPS positioning in LEO, but they have flown different satellites in GEO, basically. And I think really this was an interesting comment. If you think about GPS satellites are about 23,000 kilometers from Earth. We have some of these satellites have tracked satellites at 70,000 kilometers from the Earth. So think about the distances that are involved there, much well beyond anything GPS was ever designed to do but also GPS was not designed to work indoors. So all the work that the mobile phone companies, chipset manufacturers have done to add high sensitivity directly map in if you want to do some longer propagation delays, weaker signals kind of working from space. So all those technologies kind of fall in here. You have to do rapid acquisition, weak signal is a key piece, and weak signal and high dynamics is a very difficult kind of thing to do. So these are just a list of some spaceborne receivers. Again, this is the latest one from JPL, and Moog Broad Reach Engineering actually builds that receiver. Rug is a Swedish company with Saab. They've flown on different receivers. Astrium, Surrey is on here too. You can go to Surrey's webpage and say, okay, they have like a web order. I can go through, okay, here's a space receiver. I want to click. There's probably some restrictions to make sure ITAR certified and everything else, but you can go through and buy one online from their company if you want to go through and do that. And DLR has some great receivers too. Done a lot of work in space and seeing what happens. Not an exhaustive list, but give you some feel for what has flown, what receivers could be available if you're interested in looking at some of those pieces. So a lot of detail. We pulled some material from different people to help with this piece. There's a lot of groups here at CU which are working on this as well. Some more online resources to see what happens. Questions at all? I think there's an awful lot you can do in terms of remote sensing. And the future is limitless with what's going on with all the different constellations that are coming and how things are going to work and all the different remote sensing applications in particular. Okay, if no questions, then people can ask questions about the homework. Sarah, I'll turn it over to you to bring up something we can do that. Let me save this. Let's just say with scribbles. I'll give you this. No.
Yeah. Okay, thanks. Okay, so first of all, does anybody have any questions about the homework? Yeah.
So I just want to confirm, when you're saying for like problem 3, 2 p.m. MST, even though we are in MDT?
Yes, so that is a mistake on my part. It is actually supposed to be MDT, so daylight time. So I will send out another note to everybody, an email, making sure that you're... Sorry?
That should be easy qualifier, yes. I just put MT for mountain time, and I kind of skipped, always mess that up.
Yeah, and I totally just didn't think about that. So, yeah, mountain daylight time, so local time. Let me see if I can bring up the homework. So, let's see here. How do we get rid of this guy? There we go. Okay, so that was for all of these guys here, where it says MST, it should be MDT, local time. Any other questions? There was some here. Yeah?
When we're using the precision ephemeris, do we just use the data that's at the closest time and the time we're interested in?
I'm going to talk a little bit about that. You do not. So, is there any other questions related to things except for that? Okay.
Yeah.
Yeah.
So for like the UMA file, we're given, it comes out as longitude of ascending node,
Uh-huh.
and then, but then the rate is right ascension of ascending node. Is that
Right.
correction? Do we just use it from like the slides?
So, from the slide, so you don't actually need to take that into account. Are you talking about the first problem? Finding where all the different satellites are in what
No.
plane? Okay. Then I will talk about that in a little bit too. Okay, so let's go over, how do I, kind of lost all of the different parts here. Escape doesn't work. Uh-oh. Sorry? Alt-tab. Okay. Maybe I didn't hit it right. Okay, here we go. Thank you. All right, so first of all, let's take a quick look. I'm going to bring up MATLAB really fast. All apps, and it's under M, and MATLAB is here. Let's do this guy and that guy. So let's open. Okay, let's take a look at the files. All right, so let's first of all just quickly take a quick look at what the Almanac file says, right? So this is Almanac file. It has 32 entries for each PRN. So this is for PRN 1.
31 is missing PRN 4.
Ah, that's probably because PRN 4 might not be not healthy then. Or non-existent, yeah. So anyways, thank you. Each of these has an ID number, a health, eccentricity, time of applicability. I'm assuming you all have looked into these. You have right ascension at the week number here, argument of perigee, mean anomaly, and then IF0, which is the clock term, and AF1, which is the clock drift. And this week number is not the actual week that you're going to use, and I can talk about that in a little bit. So these are information that exists for every satellite, except for PRN4. Okay, any questions about the UMA file?
I'm going to chirp in just there, just so we're done. The UMA files are what you can download from the web. That's what everybody has. And it's this ugly text format. So if you want to work with them, it's a mess. You'd have to write all the code to parse it, everything else like that. So we try to be kind and give you all the code to parse them, so we bring them right into MATLAB. But this is how they're distributed. If you look on any sites, that's not specific to the class. That is specific to the UMA Almanac.
Exactly. Yeah.
So could you speak to the difference between the right ascension and the longitude?
Right. So the longitude of ascension, right ascension, is essentially you have your vernal equinox, and then you have the GMST, the difference between the Greenwich meridian time and the vernal equinox, and that's the longitude is actually with respect to their meridian time. So that makes sense. So here you should be getting the right ascension, so the longitude, I believe. Okay.
Oh, so we are getting the longitude.
I believe so, yeah.
Okay, so then to calculate the right ascension,
You have to take the, yeah, you have, exactly. Okay, so let's take a quick look. Any other questions about the UMA Almanac? Let's see. So let's open this guy. This is the ephemeris data file. This you can also download from the web, and I think I put the links up in lecture 13, so you all have the links in there. Let me open another file that just describes what all of these elements actually are. So let's go in here again. Oops. Not what I wanted to do. Okay, so I have a file I thought, which apparently did not get anything here. Oh, here we go. So this, if you Google for Rhinex files, this is actually a navigation file from Rhinex, so that's what we are using. So if you Google that, you can find the entire specification of what Rhinex really is. So if we go down here, and let's see if I can find it, it's pretty far down. So we're using the navigation file of a Rhinex message. And there's also an observation file, which you're going to work with for your least squares homework. Okay, so this is observation data still. Okay, so here we go. This is the navigation message. Okay, so it consists of telling you what PRN it is. It tells you what epoch you're at the received time. So time o'clock here. It tells you the year, the month, the day, the hour, minute, and second, and then it has the clock bias and the clock drifts. And if we go back here and look at that, so this is the header. So this tells you it's PRN1, this is the time, right? Year, month, date, and then this is the time, okay? So each of these corresponds to one of these guys. So clock bias and clock drift are right here. This is the clock bias, clock drift. This is the acceleration, which is 0, right? Now each of these lines corresponds to a number of elements based on the pseudo-Keplerian elements, and those are defined per line. So this is per line, tells you what it all is. So IOD, CRS, a correction term. The delta n is what corrects a mean anomaly to where you're actually at based on time from ephemeris. So that comes in where your question comes in there. Okay, so this is delta m. You have m0. All the other parameters follow the same kind of part. You can check where is each one into your ephemeris data file. Does that make sense? Okay. And you can find this by Googling it if you're interested, right? Okay, for the purpose of not having to decode all of this stuff, we gave you a file that does that, right? So if I open that guy, and let's go to broadcast to XV, this file works for both the Almanac and the ephemeris. So I modified it. For the Almanac, if some of the parameters like the correction terms doesn't exist, it sets it to 0 for the Almanac, okay? Sorry, I didn't mean to open this guy. I meant to open read GPS UMA, okay? So GPS UMA, let's just go and undock this guy. Okay. So this guy gives all of these parameters given an input file name. So you give this an input file, and you have what it gives out here, the PRN and 0. This one doesn't exist, it's blank, it's essentially 0, right? So eccentricity, square root of the semi-major axis, longitude of ascending node, inclination, perigee, all of these things, okay? So if we go and open the read broadcast, that essentially does the same thing, although it takes an ephemeris data file and puts it into the same structure. So these structures are identical except for where the parameters doesn't exist in the Almanac, you get a 0, okay? Does this make sense? Okay. So it has all of these parameters. It just essentially reads it in from the text file, okay? So if I go to my code here, I have a little demo. All right. So I just made a quick demo where we read in a file name, okay? This is for the UMA, and this is for the ephemeris. So if I put a breakpoint here and run this guy, okay? So, okay, they're right here. So this is the file name, and this is just those. And let me see what happened. So step 1, I read the GPS broadcast, right? Okay. So now this shows up. So these are my data points. And this is what we're giving to you. So if I open GPS Almanac here, it has all these columns. And it has them for all PRNs that exist, right? So all of these columns are corresponding to these guys. Okay, so you can look into which one that you need to use, and it's all here, it's all specified. Okay, whether you don't have information, it's zeroed out. So one thing that you can check is that this is the week number, and this is the time. So this was at the first time of this week. So it tells you the week number right now, or the time of week right now is 0. Okay? So, and that's all you have for this guy. And you have only one entry for the GPS Almanac. And that is valid for a long time, I think about a couple of weeks or so. Okay? Now if you go into the GPS ephemeris, it's the same structure. It also has, what did I do here? There we go. I was like, that doesn't make it look right. Okay, so these have many, many, many more entries, right? That's because the GPS ephemeris is produced every 2 hours. So you get an updated version every 2 hours. So you get 1 through 31, and then you get for the first 2 hours, and then the next 2 hours, and the next 2 hours, okay? So, and you'll also see these fields are all populated, okay? If we go in here, now I just picked a random one of these ephemeris files, and if I go into this 19, it says it's week number 1915, right? And this is the time here, so this is day 3, right? Okay. if you just do this value, 259,200 divided by 3600 times 24, and there's got to be a parenthesis here. Tells you it's day 3, okay? Now these are intervals within 2 hours, and as you mentioned, there's nothing in between. So if I go here and I open the other file that I gave you, which is broadcast to XV, this is a file. Oh, and a tip also, all of these files has a help file. So if you do help to XV, it'll tell you all of the parameters that you need to know. It's essentially just the comments in the beginning of the file. And it gives you the inputs and the outputs and everything that you need for that, okay? So this takes an ephemeris matrix. It takes a time input and a PRN, and that's actually not updated because it also has another input, because I modified this file to take either an almanac or an ephemeris, okay? So what this does is say that I want to give you any time, okay? This goes in, it reads, essentially, so you specify PRN. It takes your matrix, reads where do you have entries for this PRN, and if it's an almanac, you will only get one value. If it's an ephemeris, you'll get multiple values for every 2 hours, right? Then it goes ahead and it says, okay, you specified a time. Now, where do I find that time in this matrix? Or how much do I have to propagate in order to produce values, X, Y, Z positions in a CAF for this specific time? And that's what this file does. So you don't have to propagate anything. This file does that. So if you go in here, you will see that you find the time, you find the difference to the time, which is dt here, and then all of these values are propagated using this dt with the means and the delta means that were in the ephemeris file that you were provided with. Does this make sense? Okay. So, and it's behaving a little bit differently depending on if it's an almanac or if it's an ephemeris, because you have to choose where am I at in this time, right? So in problem, I think 8, when you are asked to use ephemeris but don't update it, then you have to go in and you have to do some modifications to this file, right? You have to think about what that really means and how do you treat your update time. Does that make sense? Okay, cool. So let me go back to my demo, which I had here. So I picked a random time, and this is 18.25 hours after GPS time midnight at day 3 in this week. So if I say that's my time input takes a week number and then the time a week. And then you specify what PRN do you want to do this for. You specify, is this an ephemeris or am I giving you an almanac version? Okay, and then you call this function and it will provide you with position right here, a velocity, and then a relativity term. And this is what you have to adjust for in your geometric range in problem 7, right? It also has a satellite clock correction that it estimates based on the almanac or the ephemeris. So you have to take both of those into account in problem 7 and 8. Before that, you don't, okay? So if we just take a quick look at what these look like. So we have, okay, we have x, right? I just showed you that. So taking the norm of x just shows you, oh, I think I'm doing the right thing and getting the value that I'm expecting. The semi-major axis about 26.5 kilometers away, 1,000 kilometers away, right? So you can make a check. Is this doing what I think it's doing, right? Okay. It also has a velocity, which we can take the norm off if we want. And then we have the relativity correction. RelCor. And then the SAT-CLK core, right? So those are the parameters that you give. So you will have to put this into a for loop when you do this for a whole week. And you will have to specify a time step. So you have to make a vector of times. A vector of your week number and your time a week. And loop through that. Okay, that makes sense? Okay. The second part is the azimuth to elevation. So if I do help plot as L, it tells me this, right? So it will tell you, this is the function name. It takes azimuth and elevation, SVS, which is the PRN number in this case, and anything else that you can put in here. You don't need this term, so you can just give it azimuth, elevation, and PRN number. And those can be vectors. So say that I give plot as L, and I give it a 35-degree elevation. That's azimuth. 300, and then 35-degree elevation, and I say this is PRN2. It'll give me a plot, and it'll tell me this is elevation of 35 at an azimuth of 300. Okay? Now what you can do is say that you want to plot this over time, right? You can give a vector. So if I do azimuth equals to, just for test, we'll do a lens space between 150 and 300 with 100 entries. Okay, that guy. And then we'll do an elevation of space. So we do 35 to 50 degrees, and we want the same number of points here. Okay, and then we'll give this guy the vector of azimuths and the vector of elevations. And that will show up in the same figure, which is here, and now I get a line. And this is how the satellite, or my fictive satellite now, is traveling over to the sky, right? Does this make sense?
So one of the key points, we try to give you the stuff that was a pain to code, that's not really related to the assignment, reading the text files, pulling out the parameters, doing this plots. You can focus on the elements I think are unique for the class, using those variables to kind of come up with where the satellites are.
And yeah.
I was wondering, like, for question 4 and stuff, when we're supposed to be propagating over time, like, what time interval should we use? Like an hour or?
An hour, so close enough to give you a good point of view. So an hour isn't close enough. I would do 60 seconds. So you get 1 point every 60 seconds or something like that. Maybe 5 minutes. So that you can clearly see where it's going.
Path,
Yeah.
Is really what you understand.
Yeah, exactly. So, any other questions? Everybody got it under control? Yeah.
When I was computing geodetic latitude and longitude, I know I was getting like I was trying to go from ECF, from what was given from Boulder, to go from latitude of Boulder to ECF and back to latitude and longitude.
Okay.
And I realized that one of them was like, one of the latitude or longitude was 75 instead of negative 105, which I know is the same.
Okay.
But off by negative. Do we have to worry about anything like that?
So I don't think you actually need to go from latitude to latitude, or from ECEF back to latitude, longitude. So just one way to do this homework. Maybe we can discuss this after class, but I think you have maybe a bug in your code. It shouldn't show up as negative 75. So, okay. Let's discuss that in a little bit. Any other questions? Okay, so for the second part of this homework, with a geometric range, you need to take into account the rotation of the Earth, right? And that's okay. Everybody's okay with that. There's no problems. Also, I want to mention something. I know most of you guys have had 50-50, and that class does a similar latitude-longitude to ECEF. You can't use that one. You have to use the WGS84. Otherwise, these parameters won't be correct. And those parameters are specified in lecture 13. So, yeah, for geodetic and just the W, the flattening of the Earth and all of those parameters, you have to take those into account. And I don't think 50-50 class does that. So make sure that if you're using 50-50 code, it won't produce the correct answer. Okay? Any other questions?
So for like problem 4 that we're plotting a lot of visible satellites, is it okay to do them all on one? Then it does get really messy.
You mean all the different?
PRN.
Yes, do all the appearance on the same plot, because otherwise you won't see what the point is. That makes sense? So you have to do all the appearance on the same plot, and you can give ASEL a vector of appearance as well. So as long as they coincide with what azimuth and elevation, and the appearance has to be connected to that. That make sense?
Yeah, just to add that, I mean, the purpose is to different places on the Earth, you get different holes in the sky. So you're just trying to represent where you see the holes based on what the constellation looks like.
Mm-hmm. Yeah. Okay.
Holes meaning, of course, where you don't have any satellites coming from that specific location.
Yeah. Okay. Any last questions? All right. I have office hours tomorrow morning, so come see me if you have trouble. And yeah.
Great, so we'll talk about the homeworks on Monday, kind of do an exam review. Exam is on Wednesday. Then the next 2 weeks after that, we have a guest professor coming from France who's going to talk about air sources, who's done a lot of work with receivers as well. Okay, thanks folks.